So far we've been talking about running time. Now we have to talk about the memory requirements of our programs as well. Well, the basics are we want to know how many bits the program uses, or bytes, 8 bits at a time. And actually we'll be talking in terms of millions of bits or billions of bits. And actually, surprisingly, there's controversy about even these basic definitions. Computer scientists think of 1,000,000 bits as 2 to the 20th and 1 billion as 2 to the 30th because that's the number of possible things that you can fit into the 30 bits and everything is consistent with our calculations. Other scientists stick to 1,000,000 and 1 billion for lots of reasons. We'll usually use 2 to the 20th to mean a megabyte. Now, on old computers, we used to, for many years, use a 32-bit machine so that pointers were 4 bytes. Just in recent years, we've mostly switched to a model where machines are 64 bits and pointers are 8 bytes. That allows us to address much more memory, but pointers use much more space. And actually this transition caused a lot of problems initially because programs were using way more space than people thought they should. You're not going to have to go through this kind of transition the way that we did because 64 bits is definitely enough to address anything that you might need to address. 2 to the 64th is really a huge number. So in terms of bytes, we have to start out with typical memory usage. Now again, this is very dependent on machine and implementation, but these numbers are reasonable and are found on typical implementations. So a Boolean, it would be nice if a Boolean just took a bit because it's just true or false, but actually usually we have to count for a byte for a Boolean. Well, a byte is a byte. Character nowadays is 2 bytes, 16-bit characters. Not that long ago, we used 8 bits for chars. Integer, regular int is 4 bytes, or 32 bits, and float is also 4 bytes. Long int is 8, and a double is 8. Usually we use doubles for floating point and ints for integers in most applications. So that's for primitive types. And then for arrays, there's a certain amount of overhead for making an array, and then if there's n items, it's whatever the cost of the primitive type times n. So an array of doubles is, say, 8n plus 24. And two-dimensional array, then, well, we can go ahead and compute the exact thing, but now it's time to use the tilde notation. Even for arrays, we could say a double is tilde 8n for one-dimensional. For two-dimensional, a two-dimensional array of doubles is tilde 8mn. And there's extra terms for the overhead, but for large m and n, that's going to be pretty accurate. So that's our basic usage for primitive types and arrays in a typical Java implementation. Now, a lot of our programs use objects like linked lists and so forth, so we have to also factor in object overhead, cost of a reference, and also there's padding built in typical implementations to make it so that each object has to use a multiple of 8 bytes. So, for example, if you had a date object that had 3 instance variables, then that object would take a total of 32 bytes. Each int takes 4 bytes. Object overhead is 16 bytes. You need 4 bytes for padding, so it's a total of 32 bytes. And the other one that often comes up is a string, and a string is a little bit more complicated than an array, but the typical implementation of a string in Java has a reference out to an array of characters, and then it's got int values for offset, count, and a hash value, and then some padding. And adding it all together, the cost of a string is about 2n plus 64 bytes. So these are the basics that we need to analyze the memory usage for a typical Java program. So for data type value, if it's a primitive type, it's 4 for an int, 8 for a double, and so forth. If it's a reference, it's going to be 8 bytes. That's what a pointer takes. Array, 24 bytes plus the memory for each entry, and an object, 16 bytes plus the memory for the instance variable, plus if there's an inner class, it's another 8 bytes, as we talked about with nodes for linked lists, and then there's the padding. Then we have to think about who's responsible for referenced objects in some cases, and we'll take care of that when we get to these situations. So as an example, a simple example of memory use analysis, let's take a look at how much memory our weighted quick union UF function from a few lectures ago uses as a function of n. And there's only a couple of memory elements, and each one of them are easily analyzed using the basics that we just gave. It's an object, so there's 16 bytes of object overhead. There's 2 int arrays. Each one of them have array overhead of 24 plus, and then 4n for the n entries. Each n of the n entries takes 4 bytes. And then there's 4 bytes for the count, and there's 4 bytes for the padding, and if you add it all together, it's 8n plus 88, which is tilde 8n. Again, all that's saying is when n is large, all we are going to care about in terms of analyzing the memory is that we've got 2 n integers, 2 arrays of size n, each one of which takes 4 bytes for a grand total of 8n bytes. Okay, so in summary, we really can figure out how many times we have to turn the crank on modern computers. We can do it with empirical analysis, where we actually execute the program to do experiments and assume a power law, formulate a hypothesis, and make predictions. But we can do more. We can do mathematical analysis, where we can identify the most costly operations, analyze the frequency of execution of those operations, and using the tilde notation to simplify analysis, we can actually explain the behavior, not just predict it. And this is a fine example of the use of the scientific method to understand the artifacts that we're studying, the algorithms. Our mathematical models are usually independent of a particular computer system and even applied to machines that are not yet built. But we always validate our mathematical models by running experiments on real machines so that we can be confident when we're making predictions and analyzing algorithms.